Hello and welcome to this lecture. So, we are now going to focus on operators exclusively. Okay, so far we have been talking about a linear transformation and its adjoint, the 4 fundamental subspaces and all the various properties it means, where what the adjoint brings to the operator and tells you more about the operator itself or the linear transformation itself. So, now we are going to focus on operators. Operators are linear transformations that go from Fn to Fn itself, right. So, when you have an operator, what about its adjoint? Its adjoint will also be a linear transformation from Fn to Fn itself, same space, right. Now, we know our orthogonality condition. Our orthogonality condition is pretty interesting, isn't it? So, you have a picture like this, you have null T star range T both being subspaces of Fn. Null T and range T star, these are also subspaces of the same Fn. I have drawn it separately here, but these are all subspaces of the same Fn now. Okay, so it's a bit of a curious thing that it works out like this. Okay, now what should happen here? Null T star has to be equal to range T complement and null T has to be equal to range T star complement. Okay, so what happens when you look at operators in especially is dimension of range T has to be equal to dimension of range T star. That also is true, right? These two have to have the same dimension, and dimension of null T will be equal to the dimension of null T star now. Okay, previously this was not true for a general linear transformation, but for an operator, null T and null T star have to have the same dimension, because range T and range T star are the same dimension. These guys have to add up to n, these guys have to add up to n, so you can't go anywhere else. Okay, so that's what's very interesting in the operator. Okay, so here are some special cases. Supposing you have an invertible operator, what do we know? Null T is 0, but then null T star also becomes 0, because range T and range T star become Fn, right? So that you can show very easily, right? So T is invertible, null T is 0, dimension is 0, range T is n, dimension n. So range T star is also dimension n, which means range T star is also Fn. Null T star is also dimension 0, which means null T star is also 0. So for invertible operators, null T and null T star is 0, range T and range T star are Fn. Okay, so we knew this before. The other very sort of trivial operator is T equal to 0, which is 0 operator. For everything you said 0, right? So that's what it is. In that case, null T and null T star will become Fn, range T and range T star will become 0. Okay, it's easy enough to see. Okay, so here are a few problems. Just working with null spaces, row space, column space, all these things for the operators. So all these dimension constraints put a lot of restrictions sometimes. Okay, so here is a way to think of those restrictions, some examples to help you think of those restrictions. So I want you to find, when this first question asks you to find 3 by 3 real matrices satisfying the following properties, or you have to argue why such a property can never be satisfied by any 3 by 3 matrix. Okay, so look at the first property. It says rank 2 with column space equal to row space. Okay, so remember, row space and null space are sort of orthogonal to each other. This is a real matrix, right? So the conjugate doesn't take any effect. So no, row space and null space are orthogonal to each other, but row space and column space may even be equal, and you can easily come up with these conditions. So don't go too far to think of complicated examples. You want 3 by 3 matrices, row space equal to column space. Just think of diagonal, So for instance, if I do this, okay, right. So this is an example where row space is span of 1 0 0 and 0 1 0. What about column space? It's also span of 1 0 0 and 0 1 0. So notice how easy it was to come up with this example. So dimension of row space is 2, dimension of column space is 2, and both of them are exactly equal. Okay, so easy to come up with rank 2. Now here is another complicated sort of example. You have to come up with a rank 2 matrix with column space orthogonal to, column space intersect row space equal to 0. Okay, so this intersect equal to 0. Okay, so rank 2 and column space and row space have no intersection except at 0. Okay, so this is an interesting little criteria. So see, row space is a subspace of R3, isn't it? And column space is a subspace of R3. and the dimension is equal to 2, dimension is equal to 2, and it says column space intersect row space equal to 0. So, these two intersect only at 0. Now, this is a very strong condition. Okay. So, this makes a lot of things not possible. So, let us say for instance, let us say row space is span of, okay, has basis, let me not just a span, has basis u1, u2. Okay. So, you know what basis is, right? Basis is, it spans the entire row space, and these two are also linearly independent. And now the column space, why does the basis have two linearly independent vectors? But the dimension is 2, okay, dimension is 2, so it should have 2. So, likewise column space is also dimension 2. Okay. So, now what will this condition imply to u1, u2, v1, v2? Column space intersect row space is 0, which means what? This, just think about this a little bit. Suppose w some vector belongs to column space intersect row space. What does that mean? W can be written as AU1 plus BU2. It can also be written as CV1 plus CDV2, right. So, that is what it means. If it belongs to column space intersect row space, it belongs to the row space and the column space. So, this implies, because of the intersection, these two will imply both of these can be written like this. Okay. Now, if it belongs to the column space and row space, if you have something like this being true, this will have to be 0, you know. Anytime you have AU1 plus BU2 equals CV1 plus DV2, you should have this being 0, okay. Otherwise, it violates the requirement that I have here. I need column space intersect row space equals 0, okay. So, what does that mean? It means you have 4 vectors here, u1, u2, v1, v2, okay, in R3, okay. So, u1, u2, v1, v2 are 4 vectors in R3. That implies they are linearly dependent. Right? If you have 4 vectors in R3, they have to be linearly dependent. So, now what happens because of that? There exists A1, A2, A3, A4 such that A1 U1 plus A2 U2 plus A3 V1 plus A4 V2 equals 0, and not all of these guys are 0, right. So, now these two you can push to the other side. So, what do I get? A1 U1 plus A2 U2 equals minus A3 V1 minus A4 V2. So, this could be my W, right. This belongs to row space, this belongs to column space, and they are both equal, which means what? Anytime I have these two being equal, then they have to be equal to 0, isn't it? They have to be equal to 0. So, now if this is 0, V1 and U2 are linearly independent, V1 and V2 are linearly independent, which means A1 equals A2 equals A3 equals A4 equals 0. So, and that is a contradiction, okay, not all 0 here, and I am getting all of them to be equal to 0 because of this condition. So, you notice how this cannot happen. So, see, this row space and column space, if they do not have any intersection other than 0, it means the basis of the row space and basis of the column space have to be linearly independent. But if they are linearly independent, they cannot be more than the dimension of the underlying space. So, if this is 2, this is 2, then that is 4, and that violates the property that these two can be 0. So, this is not possible. So, part B, this guy is not possible. You cannot have this because dimension violation will occur. Rank 2 is not possible. Can you have rank 1 with column space intersect row space equal to 0? This should be possible, because if you have rank 1, then that will work out. So, if you have rank 1, So, in fact, in any space, rank 1 matrices are very easy. Okay. So, any rank 1 matrix will have this form. It will have a column vector, column multiplied by a row like this. That will be a rank 1 matrix. Think about it, because every row, every column has to be a multiple of the same column, every row has to be a multiple of the same row, right? That is rank 1. Okay. Because just only one linearly independent row or column. So, that makes it very easy to study. So, rank 1 is always like this. Now, when I do this, supposing this is matrix vector u and this is vector v. Okay. So, usually people write this as v transpose. Okay. So, because we always think of vectors as column, no. So, my rank 1 matrix is u v transpose. Okay. So, row space is span of v transpose or v, right, and column space is span of u. Okay. And now do I mean all I need is u and v, this span and this span to have only intersection at 0, and that is possible, right. So, you have to just take u and v to be linearly independent, or you can take orthogonal also if you want to, but you just take u and v to be linearly independent, span of u and span of v will have an intersection only at 0, and that is possible. Okay, I can make these two linearly independent. So, pick u v to be linearly independent. Any u v that you can pick like this, you will satisfy this condition. So, C is possible, A is possible, C is possible, B is not possible because of the violation of the dimension. Okay. So, because of this dimension relationships, it imposes some constraints on what is possible. Okay. So, here is another little tricky question working with null spaces, column spaces and all that. So, you have to find a 2 by 2 real matrix with null space equal to column space. Okay. Now, this is also a little bit tricky. Okay. Null space equal to column space, a 2 by 2 matrix, you have to pick it carefully. We have seen an example like this before, but think about it. You can pick a column 2 by 2 like this. Okay. So, one very simple example, for instance, is to pick something like this. I think if you have 0 0 and 1 0, okay, a matrix like this. What is its column space? Span of 1 0, isn't it? What is its null space? Right, its null space is span of 1 0. Do you agree? Everything with 1 0, anything 1 on the, if you multiply on the right hand side with the column vector, the first entry can be non-zero, second entry has to be 0. So, that will give you the entire span here. So, column spaces, null spaces, then these two are equal, right. So, these two are equal. So, it's a very simple example. So, think in terms of these, when you want to come up with examples, think about a lot of zeros in the matrix and few non-zeros, you can come up with easy examples. So, the question is being asked is its left null space equal to its row space? Okay. So, you can ask that question. So, row space, just a question of this, for this example, you can easily find out this example. The span is 0 1, isn't it? Now, what is its left null space? So, you have to multiply what you can multiply on the left side, that again will be 0 1, isn't it? So, anything you multiply on the left side, if the first column should be 0, second column can be arbitrary. So, it works out. So, these two are also equal, the row space and left null space are also equal, and that has to be true, right, because see, the null space is equal to the complement of the row space, and column space is the complement of the left null space. Okay. So, if these two are equal, their complements will also be equal. So, these two will always be equal. So, this is always true. Okay. Now, question is, can there be a 3 by 3 matrix with null space equal to column space? Okay. So, this is something you have to think about. So, if null space will have a certain dimension, column space will have a certain dimension. The sum of those two dimensions, if you add the two dimensions, you should get 3. Okay. Now, if null space is equal to column space, then the two dimensions are equal. So, 2 times the dimension can never be equal to 3. So, in a 3 by 3 matrix, you cannot have null space equal to column space. Okay. Seems surprising, but it is true, right. So, if it were true, because dimension of null space but dimension of column space has to be equal to 3, and if these two have to be equal, they have to have the same dimension, right. So 2 times the dimension cannot be equal to 3. So, you can never have dimension of null space equal to dimension of column space in a 3 by 3 matrix. Interesting, right? So, such interesting conditions come when you count dimensions carefully. How about 4 by 4? And 4 by 4 it's possible, right? It could be possible. You can come up with a situation where you have something like this. It's easy to come up with an example for 4 by 4 also. I will leave that as an exercise to you. Thank you very much.